I'm going to talk to you about the Deepwave Python package that implements wave propagation as a PyTorch module. You can forward and backpropagate through it and use it just like any other operation in PyTorch. So you can use Deepwave for forward modeling, different types of seismic inversion, and it also provides the flexibility for you to be more creative, such as integrating wave propagation into a deep neural network. I'm going to divide the talk into two parts. The first will be an introduction to Deepwave, including what led me to create it, and in the second part, I'll show you some examples of things you can do with Deepwave, which I hope will give you some ideas for things to try yourself. To tell the history of Deepwave, we need to go back to 2018, to two papers I wrote that led to the first release of Deepwave. The first of these papers dealt with how finite difference wave propagation is a form of deep neural network, in fact, a recurrent neural network, or RNN. The state vector contains information needed to propagate to the next time step, such as the wavefield for the previous two time steps so that you can calculate the second time derivative in the wave equation. The input to each time step is the amplitude of the source at that time step, and the output is the receiver data recorded during that time step. It also outputs the new state vector that gets passed on to the next time step so that you can repeat the procedure. Inside the box that I've labeled finite difference time step is where the operations to calculate the wavefield at the next time step are performed. This is just the usual finite difference time step of the wave equation that you've used if you've ever written a wave propagator. It only uses simple things like additions and multiplications, the same kinds of operations that are needed in neural networks. And indeed, the whole structure is the same as a recurrent neural network. So this means that you can implement wave propagation using deep learning tools like PyTorch or TensorFlow, and because of their automatic differentiation capabilities, you only have to write the code for forward modeling, and they will automatically calculate the adjoint operations so that you can backpropagate. In deep learning, the model parameters we're normally trying to optimize are the weights in the network. With seismic inversion, the model parameters we optimize instead have a more physical meaning. They're the wave velocities, the source amplitudes, or the scattering potentials, but the procedure is the same. The benefit of recognizing that seismic inversion is a form of deep learning and so can be implemented using tools like PyTorch is that we can take advantage of all the resources that have been invested in developing these deep learning tools. This means that we can do our work in Python and still get good performance, running it on a CPU or a GPU, and we can distribute our calculations over multiple nodes. Because of their automatic differentiation capabilities, it also means that we can chain wave propagation together with other operations, such as a new idea we have for an objective function, and we only have to write the forward pass so that we can quickly test our idea without also having to worry about working out its adjoint or how to manually combine that adjoint with the adjoint of wave propagation. Another aspect that interested me was that it encourages us to consider whether advances being made in deep learning, such as new optimizers like Adam, techniques like dropout, or practices like cross-validation, could also be applied in seismic inversion. The idea of chaining together operations and being able to do forward and back propagation end to end prompted me to start thinking about what kinds of operations it might be useful to chain together with wave propagation. And that led me to a second paper in 2018 about using a generative network to do model order reduction. What I mean by that is that you can integrate a generative network into your seismic inversion to reduce the number of model parameters that you're inverting for. The velocity model we use is conventionally a grid of values, but that provides a lot more freedom than we need. For example, a randomly chosen grid of values is not a plausible seismic velocity model. Only a small portion of the possible velocity models that we can express with a grid of independent values are plausible velocity models. The idea is to use a generator that takes in a small vector, sometimes called a latent vector, and uses that to generate the velocity model that goes into the wave propagator. If there are n grid cells in our velocity model, we expect the latent vector to have fewer than n elements because the space of plausible velocity models of size n is smaller than the space of all models that have n independent grid cells. For the generator in the paper, I use a generative adversarial network, or GAN. If you're not familiar with them, here's a one-slide overview. They were proposed by Ian Goodfellow, and I think they're a pretty clever idea. You have two networks, a generator and a discriminator, which you train at the same time. The discriminator is trying to learn to determine whether the inputs to it are real or produced by the generator, while the generator is trying to learn to make outputs that are so realistic that the discriminator thinks they're real. We use this to train the generator to produce realistic velocity models, and then we discard the discriminator and just keep the generator part. So the generator now produces realistic velocity models from latent vectors, which it inputs into the wave propagator. When we perform backpropagation, we do it end-to-end, backpropagating all the way into the latent vector. So instead of inverting for the n elements in the full velocity model, we're only inverting for the smaller number of elements in the latent vector, which is why I call it model order reduction. It also means that the resulting velocity model will always be plausible. It seemed like there were lots of interesting ideas like this to try, so I wanted an easy-to-use implementation of wave propagation in a deep learning framework like PyTorch so that these kinds of ideas and other advances from machine learning could be quickly tested. I released it later in 2018 and called it Deepwave. I wanted it to be as simple as possible to use, so the inputs are just regular PyTorch tensors. The scalar, or constant density acoustic wave propagator, takes a velocity model as input in the form of a 2D tensor. In this simple example, I create a 100 by 200 cell tensor. At first I set all the velocities to 1500 meters per second, but then I set the bottom 50 cells to have a velocity of 2000 meters per second. Finally, I specify that I'll want to calculate gradients with respect to this tensor. If you haven't used PyTorch before, that's the way you indicate to it what things you want to optimize, what you're going to invert for, so that when you backpropagate, it will calculate gradients with respect to these tensors. To perform forward modeling with this velocity model, we pass the velocity model to Deepwave's scalar function. We also specify a few other parameters, such as the size of the grid cells in our model, the time sampling, source amplitudes, and the source and receiver locations. In this example, I also specify the optional PML width parameter. The PML, or perfectly matched layer, is an absorbing layer to prevent reflections from the edges of the model. Deepwave by default has a PML on all the edges, so all of the edges are absorbing, but here we set the width of the PML on the top edge to be 0, so there'll be no PML on the top edge, making it reflective. At the bottom, you can see the receiver data produced by this. With the direct arrival coming first, that's the wave that went straight across from the source to the receiver, and which in this case is very small. After that, you see the reflected arrival from the wave that went down to the interface we created between the two velocities in our velocity model, reflected off that, and came back up to the receiver. And finally, a bit later, a multiple arrives that went down to the reflector, back to the surface where it reflected because we set the PML width to be 0, making it reflective, back down to the reflector, and finally up to the receiver. I'll show you some snapshots of this wave field in a moment that should make that clearer for you if you haven't seen multiples before. Forward modeling was pretty easy, but backpropagation is even easier. We just need to specify what we want to calculate the gradient of. In this case, it's the sum of the squares of the receiver data, which would probably be an unusual thing to calculate the gradient of in seismic inversion, but that doesn't stop us. At the bottom, you can see the gradient of that with respect to the velocity model. The weak gradient contribution at the bottom of the model that you can see is due to the multiple that I mentioned. And here are some snapshots of the wave field, which we can also make with Deepwave. We see the source wave expanding out from the source. It interacts with the velocity interface, so some of the wave is reflected and some is transmitted. And here you can see the surface multiple occurring. The wave that reflected from the interface came back up to the surface, and because we made our top surface reflective by not having any absorbing PML there, the wave reflects off the top surface and begins propagating downward again. In addition to regular modeling with the scalar wave equation, Deepwave also includes Born modeling, which allows you to use Deepwave for LSRTM to do imaging. In Born modeling, you propagate two separate wave fields. One is the background wave field, and the other is the scattered wave field. The scattered wave field is generated by the background wave field interacting with a scattering model. So, in addition to the velocity model and source amplitudes, you also provide a scattering model, also known as a migrated image, as input. In LSRTM, this scattering model is usually initially zero, and then you invert for it. Here's an example of these different wave fields. This is a snapshot at a particular time where the source wave has propagated out from the source in the background wave field. It's already passed the one scatterer that I have in the scattering model, and the interaction with that scatterer acted like a source in the scattered wave field, producing the singly scattered wave field that you see on the right. Receiver data recorded in this scattered wave field looks like this, where the y-axis is time and the x-axis is receiver location. You can see that there's no direct arrival emanating out from the source, as you would expect if we'd used the regular wave equation rather than Born forward modeling. And that's because the scattered wave field only contains waves scattered by our scattering model. It doesn't contain any direct arrivals. The traditional use of a Born propagator is to invert for the scattering model, as that's what you do during LSRTM. But Deepwave allows you to backpropagate into the other inputs, and so calculate gradients with respect to any of them. Here are the gradients we get if we backpropagate the receiver recordings from the scattered wave field into the three different inputs using the model we just saw. Another feature of Deepwave is that it can record receiver data not only from the scattered wave field, as is typically done in LSRTM, but also from the background wave field. We'll see an example of using both of these features later. Deepwave also includes an elastic wave propagator. In this example, as before, I made the top surface a free surface so that ground roll will be generated, which is a phenomenon you don't get with the scalar wave equation. Moving on to the examples, the first is forward modeling. We've already seen how to do this in Deepwave with just a few lines of code, so I won't go through it again, but here's an example shot gather using a more realistic velocity model than we used before. This one is the Marmousi model. We're going to see quite a few examples of using Deepwave for inversion, so this example is meant to be a reminder that Deepwave can also be used just for doing forward modeling on a CPU or a GPU, and if you don't use the requires grad flag on any of the inputs, so Deepwave knows that you're not going to want to run back propagation, it won't store any snapshots of the forward wave field, and so you don't use any unnecessary memory. Next, we have a simple demonstration of performing FWI to invert for the velocity model. If you've ever used PyTorch to train a neural network, this should look very familiar to you. We start by specifying which optimization algorithm we wish to use. PyTorch provides all the popular ones, and here I've selected stochastic gradient descent, but you're also free to create your own. You can write your own code to update the model parameters using the calculated gradients. Next, we specify the loss function that we wish to use, also known as a cost function or objective function, and it's the same situation. PyTorch provides all the common ones, and I've selected the traditional mean squared error, but you're also free to create your own, and PyTorch will calculate the adjoint source when you want to backpropagate. We then iterate over the dataset. In machine learning, they refer to each pass through the dataset as an epoch. At the beginning of each epoch, we set the gradients of the model parameters to 0. When we backpropagate, PyTorch adds to the gradients, which can be useful if you want to accumulate gradients over multiple separate backpropagations, but it means that we do need to set the gradients to 0 at the beginning of each iteration. We then forward propagate through our current velocity model, similarly to how we did it in the previous forward modeling examples. Then we calculate the loss by using the loss function that we specified, mean squared error in this case, to compare the output of our forward modeling and the true observed data. Backpropagation, to calculate the gradients, occurs when we call backward. In this example, I then clip the gradients to stabilize the inversion because the amplitudes near the sources and receivers are so much larger than those near the bottom of the model. Finally, we use our optimizer, stochastic gradient descent, to update the model using the gradients we just calculated to reduce the loss. We keep doing this iteratively because of the loop over epochs, and hopefully in each iteration the optimizer will continue to reduce the loss, causing the model to converge towards the true model. We're going to apply that to a part of the Marmousi model. This is the true model. We'd like to get something like this as the result of our inversion. To start with, here's our initial velocity model, which you can see is quite far from the true model. And here is the output of our simple FWI. Comparing it with the true model, you can see that the near surface at the top of the model is pretty good. The sources only cover a part of the top surface, which is the reason why the result is less good on the right. In the deeper parts of the model, though, the reflectors are in the right locations, but the low wave number components of the model are missing. We just see interfaces rather than layer velocities. Making some changes to the code, which I'll show you in a moment, we instead get this as the result. You can see, if we compare with the true model, that we now recover the layer velocities quite a bit deeper than before. There were two changes that led to this improvement. The first is that the velocity model that gets past the Deepwave is now generated using this function. The sigmoid constrains outputs to be between 0 and 1, and we then scale and shift this output to be within the expected range of velocities that we've specified. We no longer have to worry about problems being caused by the velocities in our inverted model getting too high or low, as they now cannot go outside of our specified range. So I removed the gradient clipping from the code. We're now not inverting for the velocities directly, but instead we'll backpropagate to the tensor called v in this code. So this is a little bit like the GAN example at the beginning, where we were inverting for the latent vector that generated the actual velocity model. The second change probably had an even greater role in the improvement, and that was the usual strategy in FWI of inverting first for the low frequencies in the data, and then over the iterations increasing the maximum frequency. There are several ways you could implement that in Deepwave. In this example, I did it by applying filtering functions to the output of forward modeling and to the observed data. PyTorch will need to backpropagate through these filtering functions, but it seems to work well. Next, we'll look at using the Born propagator to perform imaging or migration with LSRTM. There are only three changes that we need to make to an FWI code to turn it into an LSRTM code. The first is that we need to create a new model parameter for the image, also known as a scattering model or scattering potential, so I call it scatter in this example. We initially create one that's 0 everywhere. We specify that we're going to want to calculate gradients with respect to it, and we tell the optimizer that this new scatter variable is the one we want it to update to try to minimize the loss function. The second change is that instead of using Deepwave's regular scalar propagator, we use the scalar Born propagator. It has the same arguments as the regular propagator, except we now also need to pass the scatter variable. The final change is needed because in LSRTM we record receiver data from the Born propagator's scattered wave field, but that will only include scattered or reflected arrivals. It won't include the direct arrivals that go straight from the source to the receivers. But the optimizer is going to try to make the output from the Born propagator match the true observed data, which does have these direct arrivals. If we don't do something, we will probably get strong artifacts in our image. One way to handle this is to mask the direct arrivals in the observed data. Here's what the mask that I used looks like. I apply the mask to both the observed data and also to the output from the Born propagator, even though that doesn't have any direct arrivals. I do this because the mask will probably also overlap with some scattered arrivals, so we want to mute those in both the observed data and in the data produced by the propagator to avoid causing artifacts. Running the optimizer for only one iteration, so just doing RTM rather than LSRTM, we get this as the result. There are a few artifacts, but I expect that running for a few more iterations would clean those up. An example that I think is even more interesting is to use Deepwave for joint migration and inversion, where we invert for both the migrated image and the velocity model simultaneously. This uses the feature of Deepwave's Born propagator that I told you about earlier, where you can invert not just for the migrated image, but also for the velocity model. and the ability to record from receivers in the background wave field in addition to the scattered wave field. There are again 3 changes that we need to make to our code. The first is that we now need to tell the optimizer we want to invert for both the velocity model and the migrated image, which I'm again calling scatter. Inside the loop over epochs, we pass the velocity and scattering model to the Born propagator as before, but now I apply functions to them before they get passed to the propagator. I apply a smoothing function to the velocity and a sharpening function to the scattering model. This ensures that the velocity in the propagator is always smooth. The optimizer isn't able to make any changes to the velocity model that result in it not being smooth. And similarly, the scattering model or image will never contain any low wave number features. If the optimizer wants to make a low wave number change, it has to put that into the velocity model. Whereas if it wants to make a high wave number change, it has to put that into the scattering model. We also specify where we want the receivers in the background wave field to be, which in this case will make the same as the locations of the receivers in the scattered wave field, because the final change we make is to add together the recorded data from the receivers in the background wave field and the scattered wave field. Since the background wave field should include the direct arrival, we no longer need to use a mask. Let's look at some results. This is the true model, and this is the initial velocity model that we're going to start with. It's the same one that we used in the FWI examples, and we'll use 0 as the initial scattering model. This is the resulting velocity model that we get after inversion. If we compare it with the true velocity model, you can see that it's successfully inverted to about the same depth as the second FWI example, and that's the one where we inverted for increasing frequencies, even though we didn't have to do that here. And I think the migrated image looks pretty good too. Next, I have an example of FWI using a generated model. It's similar to the GAN example that I told you about at the beginning, except that here the generator won't be produced by a GAN, but will instead be hand-coded. We're going to assume that the true model consists of layers. The latent vector that we pass into the generator contains one number for each layer, specifying the velocity of that layer. The generator will expand those numbers into a layered velocity model. This is quite an extreme example of model order reduction because here the optimizer is in fact just inverting for 4 numbers, the velocities of the 4 layers. During forward modeling, those 4 numbers get expanded into the velocity model, and during backpropagation, the gradients from the whole model get combined using the adjoint of the generating function to get the gradient with respect to those 4 numbers. This makes the inversion quite robust, and you can see that even though we began with a model that was quite far from the true model, FWI successfully recovers the true model. So far, all of the inversion examples have only used the receiver data output of the propagator in the objective function. One of the things contained in the state vector returned by the propagator is the final wave field. So rather than optimizing to match the receiver data, let's instead try to match the final wave field to a target wave field. We also haven't done any examples where we inverted for the source amplitudes, so let's also do that. We're going to try to find the source amplitudes that cause the final wave field to match a target. By now, you can probably guess what the changes are that we're going to have to make. The first is that we need to specify that we want to calculate gradients with respect to the source amplitudes and to tell the optimizer that we want it to update the source amplitudes to try to reduce the loss function. The second is that our loss function computes the difference between the final wave field and our target wave field. I also add the norm of the source amplitudes to the loss function, as I found that that gave more pleasing results. And I think this is a good example of how flexible PyTorch is. We just have to say that we want to calculate the gradient of this loss value that involves both the final wave field and the source amplitudes, and PyTorch will work out how to do that for us. That's all we have to do, so let's see how it works. This is the target that we're going to try to make the final wave field look like. It's a picture of me in front of the Alamo in San Antonio before an SEG meeting. I chose 400 randomly positioned sources and gave them 25 time steps to make this wave field. Here are a few snapshots from those 25 time steps. This is an early one where you can see the waves are just starting to propagate out from the sources. The waves continue to propagate out as we go to later time steps. At this point, you can perhaps see my head start to appear, and then we get to the final wave field, and suddenly it forms into the target image. For the final example, we'll look at graph space optimal transport. One of the main problems with seismic inversion is cycle skipping. A recent proposal to overcome this is to use a different objective function. Instead of one based on the L2 norm, the proposal is instead to use what is called graph space optimal transport to measure the misfit between the receiver data produced by our current model and the true observed data. To see the difference between graph space optimal transport and the conventional squared L2 norm, we'll first look at the value of these two objective functions as the shift between the signals that they're comparing changes. So what we're going to do is shift the red signal by different amounts from the blue signal and compute the objective function value for each value of the shift. On this slide, yellow corresponds to the traditional squared L2 norm, and green is graph space optimal transport. Zero shift, where the two signals that we're comparing are identical, is in the middle of the slide, and going towards the left and right of the slide shows what happens to the loss value as we shift one of the signals relative to the other. You can see that the L2-based loss function is not convex. There are local minima, so if we start with one signal being substantially shifted relative to the other, then it's likely that the optimizer will get stuck in a local minimum. But the graph space optimal transport loss function is closer to being convex here, so we should hopefully avoid the cycle skipping problem and be able to converge to the global minimum even if we start with a signal that is quite far from the target. Let's see what happens when we actually use this in FWI. Here we see a target signal in blue, and the red is what we get when we forward propagate through our initial velocity model. If we run FWI on this using the squared L2 norm as our objective function, the yellow curve shows the recorded data in the final velocity model. You can see that it seems to be trying to match a side lobe of the wavelet, but it's failing to match the earlier parts of the target signal. This seems like a classic case of falling into a local minimum caused by cycle skipping. When we instead use graph space optimal transport as the objective function with no other changes to the inversion, we end up with a velocity model that produces the green signal when we propagate through it. The green signal matches almost exactly with the target blue signal. The main goal of this example is not to prove that graph space optimal transport is better, but rather to demonstrate how PyTorch and Deepwave enable you to quickly test ideas. In this case, I just had to implement the forward pass of graph space optimal transport, use it as the objective function during FWI, and that was it. We've talked about a lot of things, so I'll finish with a summary. We started out with the history of Deepwave. The roots were in two papers I wrote in early 2018 that made me think it would be helpful for people to have wave propagation implemented as a PyTorch module, so they could easily try out ideas, including new ideas from machine learning. It includes a 2D scalar wave equation propagator, a Born propagator, and an elastic propagator. We then looked at several examples, starting with simple ones like forward modeling, FWI, and LSRTM. We then got onto some more interesting ones, such as joint migration-inversion, which uses the ability of Deepwave's Born propagator to record receiver data from both the background wave field and the scattered wave field, and to calculate gradients with respect to both the velocity model and the scattering potential. The FWI with a generated model example is where we reduced the velocity model to just 4 parameters that we needed to invert for, which were then passed through a function that expanded them into a layered velocity model that was provided to the propagator. Most seismic inversion examples try to match recorded receiver data to a target dataset, but Deepwave allows you to calculate gradients using any of the outputs. So in the target final wave field example, we inverted for the source amplitudes that would result in our desired final wave field, which was a picture of me in front of the Alamo. Finally, we looked at using our own custom objective function. We used graph space optimal transport, and we got a better result than the conventional squared L2 norm objective function. I'll end by saying that the Deepwave code and links to the documentation that contains the complete code for all of the examples I've shown and more are in the Deepwave GitHub repository. I hope that you find it useful, and I look forward to seeing what you do with it.